rest of chapter 12 in proportions, and we will be doing our test on Monday, and I will be sending out a letter sometime and an email sometime on Saturday telling you what's going to be in it, and hopefully you'll be prepared for it. I've changed the homework to accommodate the change in schedule, and so the homework's going to be finishing A and B of chapter 12. So let's jump right into our first question, question 10. It says, suppose that you have a one-sided test for a single proportion and that the p-value is 0.01. What would the p-value be if it was two-sided? Well, if it's two-sided, the p-value would be twice as big. So your answer would be 0.02. Now, a lot of the other questions we're going to do are involving doing the hypothesis test on WebAssign. So I've got this set up right now. And here's the first question. In the previous example, results were given for a survey of students in a statistics class who measured the length of the right and left feet to the nearest millimeter. And suppose the right and left foot measurements were equal for 108 of those times. So you're telling me that the sample is going to be 108 out of 206. So the sample size is going to be 206, okay? And p hat will be 108 out of 206. Now, assuming that this class is a representative of all college students, is there convincing statistical evidence that the proportion of college students whose feet are the same length differs from a half? And now we're going to go through the entire steps. Right, so you're going to start with p equals 0.5. And we're trying to see is there evidence that they're dissimilar. So that's p exclamation mark equals 0.5. So that's how we do not equals to 0.5. They tell us here. Now, verify that the necessary conditions are met. We are told that we can assume that the sample represents all college students. In addition, NP naught, which would be the 206 times the p naught. In this case, that would end up being, what would that end up being? It'd be 103. And 1 n minus 1 p naught would be that be 103? Let's check that. 103, yeah. And NP naught would also be 103. And these both are at least 10. So we have found that the necessary conditions are met. Now it then says calculate the test statistic, which is the z-score, the p-value, and then come to some conclusion. And so I'm now moving over to here. The guy that you want to pick to make this happen is inferential statistics, one sample proportion. In our sample, we managed to get 108 people. And that is out of a grand total of 206. And the hypothesis test is 0.5 and not equal to. And so I should be able to just go generate results. And there's our null alternate hypothesis. There's the statistic that they're asking, the z-score. Well, for that data, the z-score is that number. But to 2 decimal places, it rounds up to 70. And the p-value is this fellow. And p-value to 4 decimal places, well, that rounds up to 0. And so that passes on and becomes 6. So it finishes in 60. Now, that is not that significant, really. You can tell that's a large value, but we go through the process. The p-value is greater than the standard significance level, which in this book is called 0.05. So there is not enough evidence to conclude that college students' feet are different lengths. And we have finished our first question. So now scroll to the next one. A poll was released in the year 2000, found that 48% of 1,850 randomly selected adults, so what's that, 48% of 1,850 randomly selected adults classified themselves as very happy when given some choices. Suppose that a journalist who is pessimistic took advantage of this poll to write a headline, polls find that significant fewer than half Americans are not very happy. Well, our null hypothesis is that it is still 0.5, and he wants to prove that it's less than. And I know he wants to prove it less than because significantly fewer was mentioned. Fewer is a keyword. Now, verify the necessary conditions are met. Participants in this survey were randomly selected. NP0, which is half of that group, which is 925. And N1 minus P0, which is also 195. And I got that by taking 0.5, or in other words, half of that number. And both quantities are at least 10. So we have found that the necessary conditions are met. Now, test statistics, p-value conclusion coming up now. So we go over here. And we got a little bit of a problem, but that's what I have a calculator for. They didn't tell me how many people said yes. They told me it was 48% of 1850. So I'm doing that in my calculator. And 48% of 850 ends up being 888 out of a grand total of 1850. So if you find 48% of that number, you get this guy. Now we want a less than story, so we're going to change that to less than, so 0.5 less than, and generate results. So there's our null alternate. That matches. Our Z statistic is okay, it's not great, but it's, at least it's negative and it's got a little bit to it. And to 2 decimal places, it ends up being that guy. And the p-value happens to be this number. And if you round this fellow off to 4 decimal places, 1, 2, 3, 4, you get that. You get that guy. Now, this p-value is less than the standard significance level of 0.05. So if they mention standard significance, they mean that number. So there is sufficient evidence to be able to conclude that the headline was justified. Now, you can write down your comments about how statistically significant that is, because it's really only a couple of % shy of halfway. So it might not be that big a deal in the big scheme of things. Right, let's move on to our next one. And in our next one, we are only going to be doing hypothesis testing, single proportion B. I've moved the other one to the last week essentially, because, well, time issues. This question is question 10, so I'm going to go through this pretty quickly. It says, suppose that a one-sided test for a proportion resulted in a p-value of 0.01. What would the p-value be if it was two-sided? Well, a p-value when it's two-sided is twice what you would have got if it was one-sided. And so that's that number. That's kind of The other examples are really done using WebAssign. So I'm just going to go right into this one and show you the next question. So a multiple choice test consists of 14 questions and 5 choices in each. And the teacher wants to test the hypothesis that a student is just guessing versus the alternate one, which is the probability the correct answer in each question is higher than that. Okay. So the parameter of interest here is the probability of a correct answer on each question, right? We're interested, is it guessing? Because if there are 5 choices, wouldn't his guess be P equals 1/5, which is 0.2. But if he's not guessing, if he actually knows what the answer is, won't it be a greater than 0.2? So that's the null hypothesis, is he's guessing 0.2. And the alternate is that he knows what he's talking about. So his chances of getting it correct are better than 0.2. And we've got, essentially, click off that. We've got all the information here that we need now to do the hypothesis test, which is what's happening on the right-hand side. So let's show you where you get this guy. If you want to do hypothesis tests in SALT, hit the inferential statistics button, go over here, make sure it's one sample, and then in here, you're going to put the data. Now, what is the data? He got 8 out of 14 correct. So 8 out of 14. That's essentially your p-hat, right? 8 out of 14. Now, the hypothesis test is, the null hypothesis is equal to 0.2, and isn't the alternate greater than? It's a bit clunky, but that's how you write down this information. 0.2, and the alternate is greater than. And now I just generate results. And the p-value in this case, that's an interesting coincidence. Let's see it. Here, it's tiny. And the p-value to 4 decimal places is 0.0003. Now, from last time, if you'd watched the notes, a tiny p-value is good news for evidence, because what that basically says is that we've got evidence to prove that something is happening here, right? That the alternate is true. Now, it says, write a sentence or two about interpret the result of the p-value. So the p-value is a probability of getting 8 or fewer questions out of 14 correct if a student is just guessing. That actually got it the first time. Now, what conclusions can you make? Well, the p-value is less than, and what they're calling the standard significance level is 0.05. So whenever you see standard significance level, you know it's that number. So there is sufficient evidence to conclude that someone who got 8 correct was not just guessing correct. In fact, based on that p-value, isn't that very, very unlikely that they were guessing? I mean, you could win the lottery, probably, you know, that's guessing, right? But it's not happening typically. That format is very similar to every question that's going to happen. So I'll just move on to the next story. Suppose you're given the following information about a hypothesis test. The null hypothesis is this guy. The alternate is that. And we have a sample of 60, of which 27 out of that 60 were successes. So they're not even telling us the story. But everything we need to know is basically here. So let's figure out what the p-value is for this very vague story, right? One sample, 27 out of 60 goes here. Now, the hypothesis test is using a 0.25. And now I have to decide, using what the alternate is saying, what is here. Would you agree that the alternate is something bigger? So we use a bigger than. You say, whatever the alternate says is what this here says. So that's me putting the information. The 27 out of 60, the 0.25, and that we're looking for something bigger than that. And now I generate results. And the p-value is this guy here. And to 4 decimal places, that guy, I believe, ends up being a 2. And then you can choose one of those sentences. And that is that one done. 15 then. Like any seeds, watermelon seeds lose their viability over time. So if they've been left sitting for years, it's possible that only a small proportion of them will sprout when planted. If they have been stored in a cool, dark place, however, they have a better chance of sprouting. Seems reasonable. Drake has a large quantity of old watermelon seeds that he's been saving, and he now wants to know how many of them may still be able to sprout. So he randomly selects 75, and 42 out of 75 sprout. Now here's the hypothesis test. Is that evidence to prove that over half of them would sprout? Right, p hat is going to be the 42 out of the 75. That's his sample numbers. And I'm going to turn that into a decimal. And that's 0.56. So that's what's going to go there. Now, let's go over here and do all the other thing. Well, I guess I could do this as well. This one will be equal to, and he wants to say is over half. So he thinks it's better than half. Okay. Now, we can use this guy. One sample again. This time he managed to get, what was his numbers again? 42 out of 75. So 42 out of 75 goes here. We're looking for a 0.5 and a greater than 0.5. That's set up. So when I generate results, I get a z-score, sometimes just called the statistic. And I'm putting it here. That goes there. And to 2 decimal places, that ends up being that guy. Now, at a significance level of 0.05, what conclusions would you make? Well, it would have been helpful if they'd said to you, also tell me what the p-value is, but I can tell you it right now. Can you see it's 0.15 roughly? Isn't that going to be bigger than 0.05? So won't the conclusion be there's not enough evidence to prove that it's more than 50%? So because the p-value is greater than that number, because the p-value is greater than that number, we fail to reject the null hypothesis and conclude that there's not enough evidence. So it's that sentence there. It's the one we should be going for. So essentially you have a story where there's going to be a sample involved. The sample information goes here and here, like 50 times out of 20, 290, whatever it is. There's going to be a hypothesis. P is 0.2, or 0.6, or 0.5, and then there's going to be an alternate. It's bigger than that number, it's less than that number, or it's not equal to that number. And when you generate the results, you're essentially interested in that number. And if your p-value is less than whatever significance level they ask you to do, which typically seems to be 0.05, if it's less than 0.05, you've got evidence to prove the thing you were looking at. And if it's not, you don't have that evidence. It's a basic summary of that. Are we good? Right. I'll make up one right off the top of my head here, and we'll see how this would work out. Let's return back to the whiteboard so I can kind of do that. Oh, shooting space. I get too many things going on here. Right, someone just tried to get in. That's fine. Right, here we go. So let's suppose that we know the effectiveness of a drug, and its effectiveness is 0.83. And we think we've got a newer version, something that does a better job than 0.83, and we want to test it on the significance level of 0.01, just to be different. And we collected a sample of people, and this particular sample is only people who are getting the new drug. So we're saving money by not doing a double blind or even a single blind, but nonetheless we got our data, and it was 150 of them. And out of that 150, let's see what kind of number I should come up with here. Okay, 135 people out of that 150 lived, right? So successful, which ends up being 0.9. We're being asked, is there enough evidence using this sample to prove the new drug is better? Okay, so let's set up the null and the alternate hypothesis. Now the null and alternate is going to come out of here. The old drug was 0.83, right? 83% effective. Aren't we trying to prove that the new drug is bigger than that? Can you see why I'm choosing a greater than? All the other information that I need, I can get from SALT, but the only one that's vital is the p-value, right? Everything else is interesting, but I don't need to know it. So I'm now going to return back to our screen. And we are going to set this guy up. One sample proportion, that's good. In this case, it was 135 successes out of 150 people who took part in that drug. We are looking at the null hypothesis is that it's still 0.83. And again, we think it's greater than. So I generate results. And the p-value, which I'm now writing down, is 0.011 to 3 decimal places. So now I can return back to the white screen, and we'll come to our conclusion. Your goal is to find the p-value. If you know that, you pretty much know everything you need to know to tell whether there's evidence of anything interesting going on. We check, is our p-value less than the significance level alpha? In this case, our p-value is 0.011, and we check it against that guy. Would you agree that the answer here is no, it's not less than? Now, darn close to being less than, but that's no good to us. It's still no. And when it's no, we just basically say there is not enough evidence to show, in this case, the new drug is better. Suppose I had decided right at the beginning, before I did any of this, that I was happy with the 0.05. Right, so I made my significance level 0.05. What conclusion would I come to the second time? Would I still say there's no evidence, or would there be evidence?
There would be evidence.
Right. Because if you replace this by the new value, wouldn't you say yes? And when the p-value is less than the significance level alpha, you would then say there is evidence that the new drug is better than the old drug. And the structure of that is pretty much standard for every single proportion hypothesis test that you're likely to make. Okay, how are we doing so far? Any questions? Okay, so closing off a few windows. It's always dangerous because I end up closing off the wrong ones. No, I'm good this time. I'm now going to go back and look at some of the stuff, pardon me, some of the things that we didn't cover in A. So we're now going to look at excuse me. It's my first day back, so this is me into my hour 6, so I'm a little bit probably getting to the end of my energy level. So here we go. So we're going to do hypothesis testing from section A. And in particular, we're going to look at what's called type 1 error and what's called type 2 error. Excuse me. Oh, okay, where am I? I'm trying to find the first question that has it. And it's towards the end, but I'm not quite sure where yet. And here we are. Found one. Question 14. Right, a type 1 error and a type 2 error are when you get something wrong, essentially. That's what an error is. So let's look at type 1 error. That's when you say there is enough evidence I'm going to say the word say twice here. So there's enough in to say that the alternate hypothesis is true when in fact it's not true. You could use the word false, I guess. That is essentially what the p-value is. So your type 1 error is your p-value, okay? Now, you want that to be really small. Don't you want to not get that wrong very often? So you want that to be tiny. Now, I'll try and do a definition of type 2 error that doesn't sound like it's a lawyer. A type 2 error is when you state that the null hypothesis is true when it is not true. So can you imagine a situation where the alternate hypothesis said P is bigger than 0.7, but you weren't able to reject it? You went and said there's not enough evidence to throw it out, when in fact it was true, right? The alternate was true. So type 2 error is when you state that the null hypothesis is true. That's just another way of me phrasing that, when it is in fact not true. So if we do look at these types of errors and you put them into the context of a story, both these errors are always going to occur when you do a hypothesis test. But sometimes you want one of the errors to be as small as possible, and you're going to accept that the other one's going to get bigger. And the way it works is like a seesaw. If you make one go lower, the other gets bigger, right? If you make that one go smaller, the other one goes bigger, right? They kind of work in alternate directions. So you can't really balance both. There isn't a way to make both of them go small at the same time for a fixed sample size, right? You know, if you make the sample size bigger, all bets are off. But if you've only got a certain sample size, that's the best you can do. So let's take an example. Suppose you had a test for pregnancy. So pregnancy test looks for a certain hormone, and if it's bigger than a certain number, it means you're pregnant, and if it's less than that number, right, it means you're not. Right? So if you had a situation like that, the types of errors that you could get would be type 1 error would be you say you're pregnant. Oh, let's call H not, nothing happening, right? You're not pregnant. And let the alternate be you are. So we're not putting numbers in here, we're just kind of doing it as more generic. So a type 1 error would be when you say to someone they are pregnant, when in fact they are not. And a type 2 error would be you say you are not pregnant when you are pregnant. Would you agree that they are the 2 errors? Right. And the type 1 error is this fella, and the type 2 error is that. So now you got to decide if you're the manufacturer of this pregnancy testing kit. You want to decide where to move that little number, right? How much of the hormone do you need before you go pregnant? Because women who are not pregnant have this hormone, they just don't have as much, right? That kind of situation. Now, if you tweak one of them, won't you make the other one get bigger? So let's look at these 2 errors and see if we can put a value judgment on which one of the 2, if any, you would prefer to be smaller, even if that means the other one would be bigger. If you tell someone they're pregnant when they're in fact not pregnant, right, that's a bad thing. If you say to someone you are not pregnant when you are, that's a bad thing. But what would your value judgment be on which one of those 2 is more bad than the other? Bad grammar, but I can't think of a good way of saying it.
Saying you're not pregnant when you are pregnant, I feel like would be worse.
Yeah. Can you make health decisions based on that? In other words, go out drinking more. Hey, I'm okay, I'm not pregnant, I can party again. And you know that drinking alcohol when you're pregnant is bad for the baby, right? For instance. Or you're a heavy smoker. Oh God, I'm pregnant. I'll have to cut out the drink and smoke, right? But if they tell you you're not pregnant, you could continue. Now, what would be the disadvantage of that? Well, I guess it would give you a scare, but health-wise, wouldn't that have no real effect on your life? Because we're assuming that eventually you find out if you're not pregnant, right? You know, you do a test a month later and everything, you know, oh, okay, that was a false alarm. So you would expect then that in many situations, there may be a type 1 error that's meant to be smaller or a type 2. So if you were in this world, wouldn't you probably err on the side of not doing too many of these, right? So you might up the numbers to be a little bit more sensitive. So if the hormone level is bigger than 0.2 rather than 0.3, you know, just drop it down a little bit so you catch more pregnancies. Okay, so we got this mindset of the 2 things you can do wrong. So let's see what they look like when you do them in WebAssign. Suppose that a woman thinks that she might be pregnant, so she takes a pregnancy test. Consider the situations to be analogous to hypothesis testing. Write each of the following in words. And, well, I've got the answers here, so for speed anyway, let's just go through them then. The null hypothesis, the woman is not pregnant, and the alternate would be she is pregnant. Would you agree that would be a good way of setting up the null and alternate? Null, none, you see here. Alternate, she's pregnant. Now, the conclusion, if there is not enough evidence to reject the null hypothesis, then that would be this answer, right? The test didn't show you were pregnant. And if the conclusion is that the null hypothesis is rejected, which is another way of saying that the alternate is true, you choose that one. Now, I'm going to take out those darn answers because that one kind of did what it did. We at 13 yet? There we go. So next question, 15. About 10% of the human population is left-handed. Suppose that a researcher speculates. Actually, now I read this question, isn't that basically the same question we did earlier? So let's see if we can jump right into it. Isn't the parameter of interest? Oh, it's not. Wasn't it difference between left and right-handed, left and right feet or something? I take that back. Okay, so about 10% of the whole human population is left-handed. Suppose that a researcher speculates that artists are a little bit different from that. And so he collected data where it's 49 out of 350. Now, define the parameter. And the parameter of interest here is the population proportion of artists who are left-handed. Now, what would the null value be? Well, they think it's bigger than 10%, so the null value would be 10. And so we would say P equals 10%. And the alternate would be that for artists, it's bigger than 10%. Now, what proportion is left-handed? Well, in our sample, it's 49 out of 350. So we're basically going through the whole salt thing without doing salt. 49 out of 350, which is 0.14. Would you agree superficially that does look like there's evidence that's bigger than 10%? Now, to calculate the p-value of the hypothesis test, what probability should the researcher calculate? And make your answer specific to this situation. So the p-value is the probability that the sample would be the same as 0.10 for a sample of n equals 350. And if the population actually is 0.10. One of these is the Z-score. Sample, estimate, null value, and well, they get some weird names, but it's that one. And what's the appropriate value? Okay, we ain't going to make this. Remember we did p hat take away p naught divided by standard error. That's the guy, and that's where he goes. Now, to finish off with, I'm going to try and see if I can find some very quick null alternate guys. So I'm putting in those guys again. Okay, here is, I'm just leaving the solutions up here for you, but here is the hypothesis testing. Suppose the hypothesis test for one proportion is carried out based on a random sample and the p-value is calculated as this number. What is the, if the conclusion was wrong, wouldn't we call that a type 1 error? And there's some other ones. I wish I had more time. I apologize. The only good thing about these is there are 4 choices and you get 5 answers. So you are going to get them correct eventually. I think the best I can ask you to do is to read over some of the notes in the book. And I'm going to be doing another class right after this, and they're a bit longer. So I'm going to put their video, which covers probably more work, which will cover this stuff here. And you can have a look at that so you can see anything that you've missed. So test is on Monday. Nothing's changed, except that it will only go as far as part B. It won't do anything, including your homework won't have anything to do with it for the double proportion stuff. So that's not going to happen until after the test. On the Tuesday of next week, we're going to have another video that I'll produce, and that will cover essentially part B, the hypothesis testing for the difference of 2 proportions. And then the week after that, we only need to do hypothesis testing of means and we're finished. So that's a big, the big scheme of things. So say your last name and bye-bye. And I will see you all on Monday.